Good day everyone, we are members from Group 6 and going to present about energy balance in closed system. Energy balance in a closed system is defined as conservation of energy in a type of thermodynamic system where the energy is allowed to transfer freely between the system and the surroundings but not the mass.
Since additionally, the system is closed, no mass flows and no energy transport across the boundary take place. The general energy balance, or the first law of thermodynamics, for closed systems, can be expressed as the change in internal energy equal to heat transferred plus with work done on or by the system.
These are the history of energy balance for closed system. This law has been modified and developed by few scientists, and in 19th century, statement of the first law of thermodynamics appeared in a conceptual framework. You can pause the video if you want to learn more about its history.
Now, is about the theories. The concept of the first law of thermodynamics is applied in this case. By applying the concept of energy conservation, we can calculate the energy balance in a closed system. In a closed system, there is no transfer of matter between the surroundings and the systems, but energy does transfer between them. There are two main types of energy in transit, which are heat energy and work energy. Both of them cannot be stored in the system. They will exchange within a closed system and its surroundings. The theory stated that the total energy change of the surroundings is equal to the total net energy transferred to, or from, the surroundings in the form of heat and work, which is shown in the form of the equation written below.
From the general balance equation stated below, it shows the input and output of energy across the system. However, kinetic energy and potential energy both normally be excluded and ignored as a closed system usually presented in the static state. Internal energy is taken into account whenever we come across a closed system. Both the heat and work energy are said to follow the path function because they own have direction and magnitude from one point to another point. The final equation will be reduced to the total change of internal energy is equal to the change of heat and work energy. All the terms inside the equation must be in the same unit. Let's look at the example. Life buoy is a closed system where matter cannot flow in and out of the system. Only energy exchanges occur. Assume that the system is static with no changes in height and motion, therefore no kinetic and potential energy is observed here. Which kinetic energy equals 0, and potential energy equals 0 when the surrounding temperature increases, the heat energy will flow into the life buoy, and the pressure and volume of the system will increase simultaneously with the temperature. Work is done on the system, as heat equals mc delta T, and work equals delta PV. Thus, the system's internal energy can be defined by calculating the total heat and the work on the system. Where's internal energy equals heat plus work.
As for the sample of calculation for energy in a closed system, the question is two containers at 350 Kelvin and 0.5 megapascal each contain 1 mole of an ideal gas with a specific heat and constant pressure equals to 31 joules over mole Kelvin. The conditions are: Container A, constant pressure piston and cylinder. Container B, fixed volume. What is the temperature and pressure in each container after 8.5 kilojoules of heat are added to each? At first, we open MATLAB, and the second thing to do is to set up the variables. To make calculations smoother, you must change the unit of kilojoules into joules. Next thing to do is the derivation of the equation. The change of internal energy in closed system is equals to heat minus work. As for the internal energy for ideal gas, the equation is specific heat in constant volume times delta temperature, and it is equals to heat minus pressure, that is times to the volume delta. Derivations are then made to suit the values and the conditions given. After the derivation has been made, directly enter the name of the variables given with reference to the condition of the container. The final result is the temperature went up to 624 Kelvin while the pressure stays the same. The same concept can be applied for condition B. The difference is the fact that no work is involved in the equation, as the volume delta is 0. As for the pressure, the formula is derived as P final equals to P initial times to the division of new temperature to initial temperature. The final answer for container B is temperature went up to 725 Kelvin and pressure went up to 1 megapascal. So here are the references that we're referring to understand well on this topic. Thank you for listening.